So we have finished discussing this for the time being, but we will come back to it as we need. So next one is then knowing the slack characteristics is extremely important. And when knowing the slack characteristics, the way we define the characteristics is by its viscosity, because it's a molten liquid. So viscosity is the choice parameter or parameter of choice to describe the characteristics. So there are certain models which are available that can predict the viscosity quite well for certain types of coal ash. That's what I will first go through. What are the available viscosity models? And then later on I will show that some of these models cannot work for our type of ashes. I mean the ashes that we, ashes from the coal that we use in Victoria. So that's the purpose of this, this next few slides. There are a number of models available. The most important ones I am highlighting here. One is called the S squared model. So what it does is when you have the ash content, they convert only, they use only silicon oxide, aluminum oxide, equivalent iron oxide, calcium oxide, and magnesium oxide to 100 weight percent. So you can immediately see that this model was developed for coals which did not have much of a sodium content or potassium content in its ash. So that's why they neglected it in 1963. What is equivalent iron oxide? Dr. Davi mentioned iron may be present in different forms. So whatever forms is iron is present, total iron, just convert it to iron oxide. That's why it is called hematite, Fe2O3, and that's why it is called equivalent Fe2O3. And the viscosity, which is denoted in poise, is expressed in that formula. This is all experimental results from which they applied, curve fitting and to come to it, not necessarily any other basis really. So the denominator, the S stands for that ratio which is given in here, 100 into SiO2 and divided by that. I'm not sure exactly what was the reason for excluding alumina from there really. But the important point to note here is that this particular correlation is suited only for slags with iron and silica oxide content, silica and iron oxide content less than 55% and 5% respectively. For the other ones, beyond that, it doesn't work. See, they have the alumina in the first, when they normalize it to 100%, but in the S, they don't have it. And I have never found any consistent reason for not having it. Maybe that the curve fitting did not work very well with alumina being in the equation. So these are all empirical models, absolutely empirical models. Then I will show you how they work or how they don't work really. Then the next one is called the Watt-Faraday model, not Michael Faraday, that one, around the same time. And those proponents, they made it very clear that it works for this sort of ranges. If silica ratio is silica is in that range, or alumina in that range, or etc. in that range, then it will be this one will be valid, and that they also used a ratio where this is the weight ratio, SiO2 over Al2O3. From there, that an extra parameter that it has to range between 1.4 and 2.4. So, say for example, if silicon dioxide is 35% and aluminum is also 35%, aluminum oxide is also 35%, then the first two criteria are satisfied, but this criteria will not be satisfied, so it will not be applicable. So, and this is the formula that they came up with, where there are certain parameters called C, capital C and small m, and those are defined in that ratio, again through curve fitting and all sorts of regression analysis that they developed. This important thing to note here is that temperature is in centigrade and not in Kelvin. So we, so one of my students who worked in this area for our postgraduate degree, and went on to do very sophisticated high temperature measurements. So she did the literature review, and then her view was that the predictive capabilities of the two correlations were comparable, the first one and the second one, with higher, greater accuracy by the Watt and Faraday model for slags with high silica, greater than 80% content, or high iron oxide content. Because in our case, with some of the ashes, we had higher than silica, 80% silica, or higher than 15% iron oxide content. So that's the observation that she made. The S square method was more accurate for slags with silica percentage less than 55% and iron oxide content less than 5%. Again, that observation was made based on the viscosity results that have been published by others, and then looking at the predicted values from this one, how they match with the experimental values that have been published. And there can be one reason for contention. People can publish experimental results. Of course, any published results are peer reviewed, but often published results are refuted later on, or anomalies found in the published results later on, so that they become subject to revision. That's the nature of research. So observations are observations based on what is current. Then the next model is the Kalmanovich modified Urbane models. Urbane model was the most widely used model, actually, slag viscosity model. And again, it's a mathematical curve fitting application of the polynomial functions of slag composition to describe the pre-exponential and exponential terms of this equation, which is of Arrhenius type. So that's the nature of this equation. Again, it's from curvilinear fitting or curve fitting, but at least it comes from the Weyman-Frankel equation from physics. So take it a little bit further. This is the expression where you have on the right hand side a couple of parameters. T of course is temperature, but here in this case the T is in Kelvin. but viscosity unit is in poise. This modified Alvin model is fairly suited for coal with high silica and low FeO content. So people do look into the FeO as well when they look at the overall iron content, because that has an USTA, it has a significant effect. So the two model parameters, small a, small b, these are then given by these expressions. And there are a whole range of sub-expressions that are below. I have never bothered to investigate them in detail, to be honest. But the important thing is the last term, beta, which is present in almost all of the other coefficients that determine the parameter small b, that's actually a function of everything except silica. So that's an important observation. So what it is essentially saying, and silica is taken care of separately by capital N, and that's why the comment that has been made that it is only fairly suited for high silica containing ash, and therefore silica is not considered as a part of this function, but it is considered separately on its own by the number n in here. So these are mole fractions. Yeah, these are mole fractions. So whereas ash analysis will be usually given in weight fractions. Again, the important thing is these are all empirical values, empirical equations that they have developed. The fundamental physics behind them or the chemistry behind them are not that sound. And then the rheology. So essentially, these are matched again. These are derived from the viscosity measurements. No, it will be. These are all non-Newtonian solids. These are all non-Newtonian fluids. Sorry, these are all non-Newtonian. Absolutely. Then the next one is again another modified Alvin model, but modified by Schobert and Tritter and Dale. So they did it when the people started looking more importance to the slag from low rank coals, and the low rank coals have calcium, magnesium, sodium, potassium, iron, etc. much more than these are present in the high ash coals. Okay. So they allied the need, and that's how they actually modified it. So I have never found out the reason why they express it in CaO times CaO. Why not CaO squared? Because the result is still the same. But maybe it is like that. These are actually all in weight percents. All these all these proportions or the compositions here in each of the terms. So the Schubert-Streeter dual modified Urbane model is that's when the focus on low rank coal or lignites started. Then Kondratiev and using Jack from Queensland, they started modifying the Urbane model. They brought in a lot of science behind it, and their argument was they were working with bituminous coal. Their argument was that within the slag, even though it is molten, the proportion of the crystalline fraction does affect the viscosity considerably. So, as opposed to just the amorphous nature, and some of the compounds, slags can be partially crystalline as well, but they will still be flowing. And whether they will flow to the extent that the gasifier manufacturers want, that's a different story. It may not, their viscosity may not lie within the range specified by the gasifier manufacturers completely. So there, they came up with another version of this equation, and that's what I have given. But the major comment that I have completely paraphrased from the students' work in here, that what's the major advantage of this model, that it takes into the differences in the chemistry of the individual components without foregoing the importance of the Urbane's assumptions. However, the current study is not experimental, therefore, due to inadequate information on solid volume fraction in brown coal slags as a function of temperature, the viscosity is calculated ignoring the solid volume fraction. This will result in error where the predicted viscosity will be overestimated at the start when the solid volume fraction is high. So the point that the student wanted to make is that the Kondratiev-Jack modified Urbane model, that for the first time identified the need for accounting for the crystalline component of the compounds present in the slag. So when you have a non-Newtonian fluid such as the slag is, if it is, it may not have everything in complete liquid form. It may be in semi-liquid. Part of it can be crystalline solid. It depends on what amount of crystalline solid. That's something that it was not absolutely clear. And the other thing is, if we want to apply this model for any prediction, then we need to know in our slag what proportion will be crystalline compounds and what proportion will be non-crystalline compounds, without knowing, because that will stay between 0 and 1. Of course, if everything is crystalline solid, then the question of viscosity doesn't arise. But if it is closer to 0, then it will be close to a full liquid, if you like, even though it will be non-Newtonian. So those have to be recognized, but you can make calculations, predictive calculations, assuming 5%, 10%, 20%, etc., and then being crystalline solids, or the solids fraction, and then see what viscosity does this model predict, and then whether that matches with your expectation or not. So we'll see that. it is closer to the solidified slag. Correct. So, that's one of the points that we try to eliminate during our measurements, is that when you heat up the ash to make it completely molten, initially everything is solid. Then when you take it over the melting point, it is not, it doesn't immediately become liquid, everything. It slowly become liquid. And then, if you say, for example, if you keep the temperature high long enough at that point, then gradually the solids fraction will disappear or will reduce, and everything will become more and more and more and more liquid. So that has to be understood, that the proportion of the solid fraction is a function of time. It is also a function of temperature. If it is at a high temperature, then the solid fraction will disappear more quickly than if it is at a lower temperature, even though both are above the melting point. Yeah. So say, for example, your melting point is 1400, and you have the liquid in one case, you have the molten slag in one case at 1450, another case at 1550. So at 1450, you will have more solid fraction. At 1550, you will have less solid fraction, but both of them are molten, partially molten. If you give sufficient time, then they will be fully molten. So the crystalline part or the solid part will disappear. Now, whether that amount of time it is getting inside or not, that's the question. Ideally, you won't give it much time to stay inside the gasifier, because you don't know what it will start doing. Ideally, you would like it to become sufficiently molten and then flow, even if that means some amount of solid fraction being present, who cares? And then as long as it flows out, and but not too fast, it's fine. So in all probabilities, it will not stay there very long to become fully molten. So there will be some solids fraction remaining, that's for sure. So that's the point that the student made, that when she tried to make the comment, make the predictions for the slag from our brown coal, that I do not know how much solid fraction will be present in the initial stage. So I am assuming that it will be 0, because I am ignoring it. If that be the case, if that is error, if that is wrong, that assumption, then the predicted viscosity will be overestimated. But as long as I am making it transparently, it's known to everyone. So there is nothing wrong in saying that this is my basis. Whether the basis is correct or not, that's open to discussion, maybe open to further examination later by others. So if solids are high, solids fraction are high, then it will be very viscous. So they will not tend to flow. So they will be overestimating the actual viscosity. So the point is trying to make is, which you also tried to make, 1450 is the melting point temperature given by the database and other sources. But the database doesn't tell you how long you have to keep it at 1450 before it becomes fully liquid. It only tells you, take it 1450, it will become liquid, but definitely it will not become liquid immediately. It will become, it will be determined by the time, it will be determined how much it is there, how much of it is there. If it is there only tiny bit, then it will immediately become like that. But if it is this much, it will take a long time to get rid of all the solids. So initially, the solid fraction could be high, depending on your circumstances. If that be the case, then it will be overestimated. So before going to the next one, so there lies the very important observation that you need to make as a researcher, that to know your system very, very well for which you are making your prediction. Otherwise, the computer will simply give you a number and nothing else. So you need to know in my system how much slag I am talking about. If it is a gram, who cares? If it is a few kilograms, then I need to be careful. If it is over melting point, good. How long I expect the slag to be at that melting point, really need to know. If it is a long time, if it is few seconds, okay, that will be a problem. Then solid fraction, only maybe the outer surface is a little bit molten, but the other bit is solid. So solid fraction is very, very high. So these are some of the important considerations that you really need to know. And that philosophy applies to any research areas, not just viscosity ones. But you really need to know your research boundary very, very well. Otherwise, the predictions can be questionable. Then there are the others. This is a package called FactSage, which I mentioned before. FactSage is a thermodynamic equilibrium calculation package, but it can do a wide variety of calculations: gas, solid, solid interactions as well now. So I have given a little bit of description between it. Is it is an integration of two computational thermochemistry software package, FactWin and ChemSage. And part of it, it has a viscosity module, but it is enormous in its capability, this particular one, and that's why it is so expensive as well. That and only one module is used to predict the viscosity of different coals over a range of temperatures, and I know that they are developing it more and more and more and more over a period of time. So it is used to calculate and predict the viscosity of different coals over a range of temperatures. The second paragraph, this is entirely I have taken from the students' work. The software employs models for the viscosity of single phase liquid slags and liquid glasses. It directly relates the viscosity to the structure of the slag, and the structure in turn is calculated from the thermodynamic description of the melt using the modified Quasi chemical model. We will come to that. There are two viscosity databases. The database for melts is valid for liquid and supercooled slags with viscosities with the log of viscosity is less than 7.5, mostly corresponding to temperatures above 900. And for the database for glasses can be used for at and below the glass transition temperature. So I will come to that later. Although this database is valid over the whole temperature range from liquid melts to glasses, it is likely to be less accurate for liquid slags than the melts database. So So what they have done is they've taken very well characterized glasses first. Glasses are, different compositions of silica and alumina and few other things depending on the color of the glass. So in some ways, glasses are similar to slags or ashes. In fact, we buy glass from NIST, NIST, the National Institute of Standards, something from US. We actually buy the glass from them, grind it out, and then measure its viscosity, because they are the calibration standards. So they are very well characterized with respect to temperature, and they are very well characterized with respect to viscosity. So if your measurements are calibrated against it, just like any other measurements, any other experimental measurements, you need to calibrate it. You calibrate it against the NIST glass, NIST glass. So they have a database for the glass, and then they have the database for the melts of many other kinds. So melts for ashes that are relevant for gasification, melts that are relevant for the blast furnace application, for example, for metallurgical application. That's where the FACTS H and before that the Kondratiev Jack a modified Alvin model, they started. Previously, everything started for coal combustion to find out the liquidus temperature, the fluid temperature, the melting and its viscosity, etc. Then gradually it moved to the more development started taking place when people started looking at its applicability away from coal combustion to metallurgy and then to gasification slag. And that's where it's called the MELTS database. So the MELTS database you can actually see upon checking with the software supplier, FACTS H supplier, it's a Canadian one, what is actually in their database and for what range of silica, alumina, etc. do they say that their predictions are good, and then immediately it becomes obvious to you whether it is suited for your need or not. So we then looked at this. Let's go back to one other point there, the modified quasi-chemical model. When you have a mix of all sorts of chemicals, these are all independent chemicals, if I may say so, the silica, alumina, magnesia, calcium oxide, etc. So, but chemicals, we are also normally associate ourselves with, the acids and bases and etc. But in general, you can argue also that these are also chemicals. These are also chemicals because these are all compounds of chemical elements. But to differentiate between those, the conventional types that is in our perception and these ones, they use what is called the quasi-chemical model. But there is another important distinction as well, which I will have to find out. I cannot recall. So can you write in that piece of paper quasi-chemical model, and then I will come back to it on Monday. Quasi-chemical model. So there is another important aspect to it, which I forgot now. I will have another look at the work. It is very well explained there, and then I will come back. So that will be number 3, right? Okay. So anyway, so having looked at these 6 major ones, then we thought, okay, let's try to apply it blindly. because all it needs is the knowledge of the ash composition determined by X-ray fluorescence expressed as in oxide form, nothing else. And then the rest are all algebraic manipulation. You calculate one parameter from the other, another parameter from the next, another parameter from the next, as you have seen in all of these models. These are nothing but a collection of large algebraic expressions, nothing else. So it's simple Excel calculations. You are not doing anything other than that, all as a function of temperature. So she did this for one of our coal ash, which is the high iron containing ash, the Alvin ash, as we mentioned before. So here you will see the different predictions, the S2 or S squared correlation, Watson-Faraday, Kalmanovich, Schubert-Streeter-Diel, Fact-Sage melts and Fact-Sage glasses, Kondratiev and Kondratiev-Jack, etc. And by using the composition for one of our ash. And then she plotted them over the temperature on the x-axis and viscosity over the y-axis. Now, these are all predictions, comparison of predictions from different models for the same ash. So same ash composition given to different models and calculate no, there is no experimental data here at all. These are all predictions. So there are about 1, 2, 3, 4, 5, 6, 7 different models that have been utilized to predict the viscosity. Very difficult, but so easy. There is no experimental. How do we so we are not concluding anything. We are concluding that this is garbage. Because it is giving us so much variation. So this is telling us for our ash that some of which will give you 100 points viscosity. So take one of the horizontal lines. So one model is telling you it will give you a very low viscosity, that means a really smoothly flowing at 600. And then another one is predicting that you will have to go to about 1500 in another one. And the other ones are all lying there in between. We know very well that 600 nothing happens. We generate ash at 600 running. So which one is correct? So yeah. The only conclusion I make is this one. None of these are conclusive. None of these are matching our requirement. And the other thing that we also looked at, remember in day 1, day 2, very beginning, we talked about ash fusion temperature. And there we talked about 4 different temperatures. Initial deformation temperature, then another one, the second one is hemispherical, then the final one where it absolutely melts. So and those measurements can be done in either reducing environment or in oxidizing environment. In reducing environment, the temperatures are lower. The 4 different temperatures are lower compared to oxidation environment, which means that in gasifier, this will be the case. Where you have a reducing environment, therefore they will be the ash will be melt at a lower temperature than inside a PF fired combustor. That is fact. But ash fusion temperature, the last of the ash fusion, 4 ash fusion temperatures, gives you the melting temperature, because that is what you can see when you put it in a hot stage microscope. You can actually see the cone gradually deforming and then disappearing into a liquid. Here, that observation falls between these two. So, that ash fusion temperature falls in between these two, temperature wise. So, you can say that yes, it will melt at that temperature, but is that good enough for gasifier use, for use in design of the gasifier? Because what I said, the melting is a function of temperature and time. It can melt at beyond a certain temperature, but it cannot melt fully at that temperature unless you give it sufficient time. So, the ash fusion temperature measurement is not the sole predictor, it is a complementary first cut information, and then you need to see the predictions, what it is telling you, because these predictions from the models, the way they are plotted, on the y axis you have the viscosity, and the gasifier manufacturers tell you that we need a slag at a viscosity between 100 and 250 poise, which means 10 to 25 Pascal second, that 25 Pascal second, that is the upper limit. So, if I look at in here, where is 250 Pascal per second? 250 Pascal per second. For these two apparently matches my ash fusion temperature predictions. And then I look at the lower limit and then the upper limit of temperatures for the 100 to 250 poise, which is dictated by the gasifier manufacturers. I see that the temperature here is actually quite low, and at that temperature it will be semi-solid, it will only be partially melting, and possibly, even though that is what the model is predicting, it will not actually flow down. So, what is the conclusion? The conclusion is ash fusion temperature is giving us some indication. The predictive models are telling me that majority on the left, the first 5 are completely useless, because that does not match my expectation based on my expertise. The other 2 may be, but I am not sure. So, that is the conclusion. So, what is the next step? Next step is go for experiments and then sort it out, and then find out what is the actual viscosity. So, here is a classic case for the researchers, a dilemma that you need your models. Without models, you could not come to this, but models are not everything on their own. You really need to look at what the models are predicting and then the final decision is made by you, who knows the system, who knows the coal, knows the ash, knows the gasifier system very, very well. And that's the common mode of inference making across any disciplines of research. Models are models. They are only one tool. Ultimate use of the models is through the predictions, and then you, if necessary, you modify the models to suit your case with proper basis. So then we started preparing for the experiments, and that experiments are not very easy. I can tell you why. As you said, you have to create the environment that exists in the gasifier. Number one, reducing environment, easy. I will not feed any oxygen. I will make sure that there is no oxygen. I will make sure that there is carbon dioxide and other gases. The other gases in gasifier are carbon monoxide and hydrogen, but I cannot put carbon monoxide and hydrogen inside that environment without looking at their lower and upper flammability limits, because no safety committee will permit you. Now, in a gasifier, you have say 40–50% hydrogen sometimes. At least we got for fluidized bed gasification 25% CO, 25% hydrogen. Those are right in the middle of the lower and the upper explosibility limits of hydrogen, so you cannot use it. So you have to go for hydrogen. The lower flammability limit is about 4%. So if you want to put in hydrogen, then you put below 4%. Now, and similarly for CO, then it's for CO2 not a problem. CO2 you put in 100% CO2, not a problem. So during the measurements, then what you need to do, what we then made a careful decision. Okay, we cannot put hydrogen because these experiments will take very long time. Because not only that we will have to melt them, but we will have to make sure that they melt melt fully, which is a function of time. And we don't know how long will it take to melt. It could take 8–10 hours to melt, and literally they do take 8–10 hours to melt, and we found it in the wrong way, in a very difficult, through a difficult exercise. Then CO, so hydrogen and CO, we decided that because we will have to do the experiments over a very long period of time, each experiment, if it is successful, will take 16–17 hours. We cannot afford to have hydrogen and CO going there for 16 and 17 hours during that, at that temperature. If anything happens, I will spend my life in jail. So we made the conscious decision that we will do everything inside CO2 environment. Then the question then is, what material do you select that withstand that kind of temperature for that long? Also that material has to be something which is not present in the coal ash. So none of those that you see in the coal ash should not be. So I cannot use a silica crucible, as simple as that. That would have been cheaper, very cheap. I cannot use an alumina crucible, that would have been cheap. Unfortunately, can't because it's there. The only thing then we found was the molybdenum. And each molybdenum crucible costs about $200. So, if an experiment is not successful, you lose your molybdenum crucible. But then the other most important thing is getting rid of oxygen. Oxygen can penetrate anywhere, anytime it likes. And a furnace where you have to create an atmosphere of 1600 degrees in order to have that temperature in the ash, which is a thermally insulating material to start with. Outside is the molybdenum crucible's wall, which is another insulating barrier, and then outside which you have to supply that heat. So, just you can make a simple heat conduction, one dimensional heat conduction calculation to see, in order to have my ash internally at that temperature with all these insulating barriers, what should be the heat. So, we had to buy a very expensive high temperature furnace, but 1800 degrees it can go, 3 phase, which requires 63 amperes of current. These are only 10 amps, 63 amps, 3 phase. We have to change the electricity cables, because you are now looking at long, large cables, because the current carrying capacity has to be reflected in that. So, a bit of interaction with the electrical engineering people. And then the biggest challenge is how to scavenge all the oxygen, otherwise oxygen will eat out the molybdenum. So, we eventually decided that inside the furnace, closer to the vicinity of the molybdenum crucibles, we will put in graphite blocks that will last for about 20 hours. The graphites will soak out the oxygen before they come in contact with the molybdenum, and then that way we will do it. But so that became a lot of exercise in doing it, and then finding out, and then perfecting it that way. But then the biggest issue then is you have to ensure that the liquid has become liquid, even though it is knowing fully that it will be non-Newtonian liquid inside the crucible. How do you know it? Because you can't see it. Everything is sealed. The viscometer assembly is dropped from the top, perfectly sealed so that not much air can go in, and then the spindle, the viscometer knob, the rotating knob has to rotate, and if you lower it early enough, and you don't know what is early enough, then it will be going to a semi-solid, and it will not rotate anymore, and therefore the experiment is gone. So, you have lost your molybdenum crucible, that is $200. The rotating spindle and the knob, that is another $400, those are gone. And then one research assistant, more than 1 day's 2 shift work, they have to be paid extra amount for working after 5 o'clock overtime. So, these are all gone. So, you learn it at the hardest way, but you need to do it that way. It's a very, very difficult set of experiments that one can do. That is why the need for development of the models. Anyway, we did it over about 3 years. We perfected it. With a lot of money and blood and sweat, student living, supervisor persevering with someone else, and because it has to be done. And then the important thing is, once you find that you can measure it, then you get the data, then the question then is how you will relate it to the chemistry of the liquid, which unfortunately has changed because it has stayed at that temperature for a long period of time at that temperature. So, mineral transformations have also taken place. So, that has to be captured somehow. So, you have to get the, after the experiments are done, everything has to be cooled down, the crucible has to be retrieved very carefully, and inside all you can see is like cement, and a distinct boundary of the solidified slag. So, you take it out, subject it to XRF, subject it to EDX, subject it to X-ray diffraction and all the associated preparations, then put it in FactSage again, put it to phase diagram, get all the compounds, elemental and the compound information. Everything is crystalline, that is the beauty of it though. And then try to relate it with this, the viscosity, because your starting composition is no longer valid, even though you can try to relate it to the starting composition. But that lies a challenge. It's a phenomenal effort that one needs to make just for coming to terms with one aspect, which is the viscosity of the slag, whether it will flow or not for our type of coal ash, because no information was available, no one did it before us, and now that it is all done, it has been accepted by the Japanese, and they are now forging ahead. They are now confident that now we know what temperature we need to have to maintain at the lower end of the gasifier, where slags will form, where slags will be taken out as molten slag, and so it's good. So, here is, because it's all paid work, so I cannot show all the work, but this is just one sample, and there's a whole lot of story that I can tell in about a 200-page report that we eventually gave, but it's a commercially sensitive report, so we can't publish it. But it's a very big piece of work that we undertook. And so, here is we eventually said that, look, this is the temperature region for this and this coal mix, this and this ash mix of this type and that type of coal, and this is where you will get your 100 to 250 poise viscosity in the temperature range. So, if you operate within that, then you will get a slag out. The only other thing that you have to ensure that these temperatures are good enough to give you highest carbon conversion, right. So, that actually completes the whole holistic story. So, I am not sure whether you are able to fully appreciate this. There is a lot of stories and issues in gasification, not just some experiments finding the gas composition and carbon conversion. That is one side. That has to be complemented with this side, or if you have done this side first, then you have to complement it with the other side. If these two requirements do not match, that means your carbon conversion temperature is way less than the slag viscosity temperature requirement, then it becomes the issue for the technology developers to design their gasifier in a certain way. That is their headache, not my headache. So, in the main reaction zone, if I recall the two layers, two stages that you showed, that's where you have to ensure that everything gets gasified. That's why you also have to see that at least in the bottom part of it, when slags will be more and more, you will have to ensure that this temperature is at least maintained.
So, it is a downward gasifier and the it is slow burner. Then there will be combustion zone before, then there can be gasifier section. So, generally in the gasifier section at the bottom part, exit the temperatures are about 700 degrees centigrade, 600 degrees centigrade or so. So, there the slag will not be flowing.
So, there you have to get
back to the discussion on the different types of gasifiers. If you can recall the Siemens gasifier that I talked about, where they inject a spray in the middle, they started doing it for condensing of the airflow. What it also does there is it also breaks down the slag there into smaller particles. They then fall and they come up as so small particles and they're easier to distance their point. I haven't seen it, but I'm sure that they also do, otherwise they could not have gone to 400 megawatt. They have carbon conversion rate.
This response comes for both like combustors and gasifiers.
Now, combustors is slightly different. So pulverized coal fire combustion. There, your ash is melting, but it is taken away predominantly into the other sections where it is being depositing onto a plate and then reheaters, etc. While going regular intervals to do it. In one manufacturer's design that I have seen in an operating plant, I can't name it, as the slag falls from the gasifier, as the slag falls, they quickly inject high jet water, and they quickly break down the falling slags, otherwise there is a big chance. And simply by quenching it, because of troubleshot, they disintegrate that while it is converting from liquid to semi-solids to solids.
We have our temperatures ahead of because we have certain engines like cement.
Here, fire, this sort of problem should not be there.
We don't need slag there, slag. And now the position of slag we can use in the
So, the moral of the story is that we need both modelers and experimenters for most reasons. And we need to appreciate
the nitty-gritties of both. You cannot say that the experimenters are rubbish, modelers are good, or experimenters are good and modelers are rubbish. You need to know the fundamentals of everything. Then only you can solve any problem if you like. Difficulty will be there. Nothing is easy. I mean, it becomes easy if you take it easy and in good spirit. But it's very important to understand the fundamentals behind everything. Then you can devise a solution, engineering solutions, which only comes from fundamental understanding of the science behind it. So everything has followed from ash chemistry actually, as you can see. So there at the bottom of the furnace, there is something called bottom ash hopper, which is actually the ash is dumped in water. So that, because just imagine otherwise hot ash falling, they will disperse everywhere. So if they fall in a trough of water, a considerable trough of water, then that's where they will immediately quench and they will solidify and they will not be able to fly out. The hot ash not flying out anywhere and creating fire hazard. That's what in the bottom ash. What goes over, those are cleaned up by the wall blowers, retractable soot blowers, etc. And those then eventually make their way out to the ESP or the back filter. And those which are deposited on the wall, which are cleaned by the wall blowers, retractable soot blowers, time to time. And those which fall down are collected in the bottom ash hopper in water. And then periodically those are discharged away. So that's a normal part and a very manageable, established part of plant operation, boiler operation. There's no risk in it, manageable risk in it, but right.
And then it created a lot of water vapor, and that going inside the furnace, and it pressurized it.
So there lies the need for very regular observation and maintenance. These are high temperature, large high temperature equipment. They have to be respected. In some ways they have their own brain. If you neglect them, they will take advantage of it.
So as you said that once we have in the scoping measured viscosity, then we have to track it to the chemical composition will change because of mineral transformation. So how you will track it back? Because initially we have asked for different composition, then it changes after being more than how we have track it back.
So easy. As I said, you track it back to its original composition. So you plot this viscosity as a function of its original composition. You would also plot it as a function of its current composition. But I can show you.
After heating, we can measure its viscosity. Initially, how we can measure? Initially, we
No, viscosity we are measuring for when it is liquid. But we have done relating the viscosity to its original composition before it was liquid. Because that means when it was ash.
that composition into liquid.
So only that composition went into liquid and then became another composition. So as long as you plot this viscosity against both of those compositions, even though they have changed, that's fine. And you can get a lot of insights, mechanistic insights from that. That will require a fair bit of other fundamental that in itself is a PhD project. But if everything has an embargo period, that's why I've been very careful as to what I think I'm giving the final question. To the last slide. Any other question? So maybe we'll adjourn for lunch now. After lunch, I intend to start on the other big topic, which is the gas cleanup. It will not be finished today for sure. But most possibly will require a good part of Monday as well. And I also intend to spend a little bit today, if I can, on the follow-up questions on the parenting thing. A few more slides to make on the lunch just to discuss that. If these two I can start and complete what I want to do a little bit on the gas cleanup, and then that will then I will run out. So that's it, and then Monday after that one we will be moving on to the more advanced cases, toxicity, chemical loading, cold chemicals, synthesis, and all those sort of things. And gasification will most possibly become history. When are the students presenting again?
So I think
let's keep it very simple. It's as you can see in my presentation style, it's more like an informative, knowledge sharing mode. It's not classical teaching mode that I'm presenting, that I'm doing, and it's not. And this is not an undergraduate class. This is a workshop. So keep that in mind. So present whatever you can, so that we become, all of us can become knowledgeable in what you are doing, and hopefully giving you some ideas for you to either consider or discard.